Hello everyone, welcome to PW. Good evening everyone. Please let me know by writing in the comment section whether audio and video everything is perfect or not. Great. So now we are on very important lecture, and in this lecture number 14 we discuss about the sequence detector. We also see about 1-bit overlap, 2-bit overlap, what is a sequence detector, and overlapping in a sequence detector, what kind of questions are asked in this particular topic. We will see all of these things in this particular lecture. So all of you are ready? Please let me know by writing in the comment section, beta ji, that audio and video everything is perfect. So now we are on lecture number 14th, and within these 14 lectures I have tried to cover the entire things of the digital, okay, which is required for your exam. Maybe your branch is CS, maybe your branch is ECE, IN or EE. So for all branches, this course, this rapid course is sufficient if you are going with this course along with the PYQs. Is it okay? That's all you have to do. Now please observe what are the topics today I am going to discuss. The first one is state reduction. Second one is finite state machine, part 2, where we will discuss about the sequence detector, okay, by using Mealy model as well as by using Murray model. Now please observe first state reduction. Why we need state reduction? Basically, whenever a user come to us, us means I am talking about designer. Whenever a user come to designer and ask to design some desired circuit, then as per his condition, there is a possibility that for the same input, same next state and same output may appear. So we will examine this in the state diagram, and then we can remove the particular redundant state. If the two states will have same next state with the same input and same output, then we can remove one of the state. Is it okay? This reduces the number of flip-flop required to design a particular circuit. We all know, to design any circuit, how many number of flip-flops are required? With the relation m is less than or equals to 2 to the power n, where m is the number of states and n is the number of flip-flops. So, number of states and number of flip-flops. Definitely, if you are reducing the number of flip-flops, it means you are reducing the cost of the circuitry and complexities of the circuitry. Is it okay? Yes, sir. Now, please observe state reduction. Very important for your state machines. Basically, it avoids the introduction of redundant state. Redundant means not necessary states. Please let me know by writing in the comment section, beta ji. All of you, please let me know by writing in the comment section that audio, video, everything is going perfect. Okay. Basically, it avoids state reduction. Basically, it avoids introduction of redundant state. The reduction of redundant state reduces the number of flip-flops required and the logic gate. Hence, it reduces the cost of the final circuit. So now we know what is the purpose of state reduction. Now, how to do the state reduction? If two or three states, one of 2 or 3 states is said to be redundant. One of 2 or 3 states are said to be redundant if every possible set of input generates the same output and exactly the same next state. Is it okay? Yes, sir. If two states are equivalent, then one of them can be removed without altering input-output relationship. So now we know what is the purpose of state reduction. Let's understand with the help of one question. Okay, let's understand with the help of one question. Suppose a user asks to design a particular situation, a state machine for a particular situation. Okay, please observe here. Find the reduced state diagram for the state diagram shown in figure. So we have to identify the reduced state diagram. But before finding reduced state diagram, by observing this state diagram, you have to tell me how many number of minimum flip-flops are required to design this particular state machine. Okay. So as per the given state diagram, how many number of states are there? Number of states are there A, B, C, D, E. So total we are getting 5 states. And since we know m is less than or equals to 2 to the power n, so n must be equals to 3. It means if you have to design a state machine having 5 different states, then minimum number of flip-flop required will be 3. Minimum number of flip-flop required will be 3. How many of you able to understand? Yes, sir. But we need to examine this particular state diagram. There may be a possibility that for the same input, we are going to the same next state and same output appears. So how to examine that? We have to draw the state table from the state diagram. Please observe here, Betaji. If you are on state A, then input x is equals to 0. Input x is equals to 0. You go to state B and output will become 0. If you are on state A with input x is equals to 1, next state will become C and output 0. If you are on state B with input x is equals to 1, next state is E, output 0. With x is equals to 0, next state is D, output, let me check, output 1. Okay? Yes, sir. If you are on state C with input x is equals to 0, with input x is equals to 0, next state C, output, with input x is equals to 0, next state C, output 0. If you are on state C with input x is equals to 1, next state D, output 1. If you are on state E with input x is equals to 0, next state C, output 0. If you are on state E with input x is equals to 1, the first term of this oblique sign is the input and the second term is the output. Arrow indicates going to next state. Is it okay? Already Mealy model we have observed in the last class. Okay. Now with the present state D, input x is equals to 1, state will remain at D, output 0. Present state D with input x is equals to 0, next state A, output 0. Is it okay? Yes, sir. Now we have to identify which, or there may be a possibility more than 2 or 3 states having same input output relation and going to same next state. In order to understand, first of all, we need to draw the state diagram from state table from the given state diagram. So state diagram is given to you. State diagram is given to you. Now you have to draw the state table. Okay. Yes, sir. Let's draw the state table. So if you observe state table, yesterday I have discussed about the state table as well. In state table, we have a input. So here only one input is indicated. This is representing present state. Present state. This is indicating present input and this is indicating output. Arrow indicate going to next state. Is it okay? Now please observe here. So present state. Present states are A, B, C, D, E. So I am representing A, B, C, D, E. A, B, C, D and E. We have total 5 states given. Okay. Yes, sir. I need your response, Betaji, in the telegram, in the comment section. Please mention that everything is going perfect. Audio, video is perfect. Okay. Great. If the present state is A, next state with x is equals to 0. Present state is A, x is equals to 0. Next state is B, output 0. Next state is B, output 0. So next state is B, output 0. How many of you able to understand? With the present state A, input x is equals to 1. Present state A, input x is equals to 1. Next state C, output 0. So C, output 0. Present state B, x is equals to 1. Next state E, output 0. It is D, na? Let me correct it, beta ji. With x is equals to 0, next state is D output 1. D output 1. With x is equals to 1, next state E output 0. So next state E output 0. In the same way, if you observe for C, present state C, x is equals to 0, next state is also C output 0. Next state is C output 0. Present state C, x is equals to 1, next state D output 1. So present state D, x is equals to 0. X is equals to 0. Next state A, output 0. Next state A, output 0. Present state D, x is equals to 1. Next state D, output 0. Next state D, output 0. Present state E, x is equals to 0. Next state C, output 0. Next state C, output 0. Present state E, x is equals to 1. Next state D, output 1. Next state D, output 1. If any 2 or 3 rows are absolutely equal, then that indicate out of the 2 or 3, out of the 2 or 3 rows which are being equal, you can take only one, considering all other redundant, because they are giving same next state and same output with the same input. So if you observe in this particular question, we have C, state C and state E are equivalent states. It means if you are on state C, with x is equals to 0, you will reach to C and output 0, and x is equals to 1, you will reach to D and output 1. Even if you are on state E, with x is equals to 0, you will reach to state C, output 0, and with x is equals to 1, next state D, output 1. So C and D states are equivalent. One of them can be removed without altering input-output relationship. Is it okay? Because one of them is a redundant state and we can reduce the state table. So, how many of you now able to understand, beta ji? Please let me know by writing in the comment section. How many of you able to understand now? E and C are equivalent state and one of them can be removed. Let E is being removed. In other places, we have to change E with C. So now please observe here, I am going to reduce the state table. So the reduced state table will become, sir, we have a state A, B, C, D now. With the state A, B, C, 0, 0. So this will remain B, C, 0, 0. And with the state B, D, E, 1, 0. So D, E is replaced by C, 1, 0. Here, E is replaced by C. Okay? Yes, sir. CD 01, CD 01, and the last D is AD 00. AD 00. How many number of states are now? This is your reduced state table. By observing this reduced state table, we can have reduced state diagram. So if we talk about reduced state diagram, please observe, beta ji, I need your response. So we have now state A, state B, state C, and state D. With state A, x is equals to 0. Next state is B, output 0. With state A, x is equals to 0, next state B, output 0. So next state B, output 0, and with the present state A, next state is C with x is equals to 1, output 0. Next state is C, output 0 with x is equals to 1 for a present state A. Now again observe, present state B with x is equals to 0, next state D, output 1. Present state B with x is equals to 1, next state C, output 0. X is equals to C, x is equals to 1, next state C, output 0. Present state C with x is equals to 0, next state C, output 0. Present state C, x is equals to 1, next state D, output 1. How many of you able to understand? Present state D, x is equals to 0, next state A, output 0. Present state D, x is equals to 1, next state D, output 0. So how many number of different states now? The same state machine can now be designed with the 4 states. So m is less than or equals to 2 to the power n, that indicate n is equals to 2. So by reducing the state diagram, you have reduced the one flip-flop required, and accordingly the delay and complexities of the circuit get reduced. How many of you able to understand, sir? Can you please explain again? I can't understand. Sai Kumar, what happened, beta? What you are unable to understand? See, what is a state reduction? A state reduction means, see, whenever a user asks to design any desired sequential circuit with a designer, then there is a possibility user unintentionally give more than same situation to the designer. So designer will examine all the situations through a state table and then make a reduced state diagram. That reduced state diagram, when designer going to design, the cost of the circuitry will be lower because we may reduce the number of flip-flops and logic gate. State reduction technique says in a state table, if two rows are absolutely similar, then the two rows are said to be equivalent and one of them can be removed without altering input-output relationship. So here we have a given state diagram. This state diagram is the desire of the user. If designer directly implement, then number of flip-flop needed will be 3. But designer now examine this, is there any possibility of repeated state? So that can be concluded with the help of a state table. In the state table, from the state diagram, we have drawn the state table. In the state table, we have observed C and E are equivalent states. So one of them can be removed. So we are removing state E, and wherever E is there, apart from E state, we have to replace E with the C. Is it okay? Yes, sir. Now, if you observe, we have only 4 different states left out, A, B, C, D. So only 4 states. Always remember, in this oblique symbol, this one is representing input. Okay. This one is representing output. This one is representing present state. For a moment, please observe here how we have designed. Present state A, input x is equals to 0. Present state A, input x is equals to 0. Input x is equals to 0. Next state will become B and output will become 0. So next state indicated by the arrow and output indicated here. How many of you now able to understand? In the same way, the entire state diagram I have constructed. Is it okay now, beta ji? Please let me know. Is it okay now? Are say in yes or no, beta ji. Is it okay now? Great. Sai Kumar, you have asked to explain once again. I have tried to explain you entire things again. Are you able to understand now? Okay. So now we know about the state reduction technique as well. Next, let's move towards the sequence detector. Is it okay? Yes, sir. Now let's talk about sequence detector. Sequence detector. Please observe, sequence detector. Sequence detector. Mostly sequence detectors are used to decode some specific codes or mostly used in digital data transmission. Okay. Now please observe here how a sequence detector will work. We may have a 1-bit sequence detector. What is a 1-bit sequence detector? Please observe here. In a 1-bit sequence detector is used to detect the specific input sequence in a clocked synchronous sequential circuit, mostly used in digital communication to detect the digital messages. Now please observe how it works. Suppose we have given a digital message as, suppose we have given a digital message X as 1011. Okay. Suppose we are going to give the digital message as 1011. Let me increase further. Say 1, 0, and so on. Suppose we want to design, we have a X, okay, and X is applied from the MSB side. So this MSB side, or you can say the first data which goes on to the input is this. Then on next clock pulse, this data will come. Then on next clock pulse, this data is going to apply onto the X. So X data is applied here from MSB to LSB. This side, the data applied sequence. Okay. Suppose the data is applied in this sequence. I have represented left to right. Okay. So first this data, then this, then this, then this, then this, then this, and so on. Is it okay? We have a 1-bit sequence detector to detect sequence 1010. It is a specific sequence detector circuit which going to detect a particular sequence 1010. Whenever the 1010 sequence will come, then output will become high. Otherwise, output will remain in low state. So now please observe here. Output becomes logic 1 only when sequence got detected. In case if the sequence is not detected, we say output is logic 0. So now please observe here. First I am using a non-overlapping NL type. What is NL type and OL type? We will discuss later on. But just understand it is a NL type, that is non-overlapping sequence detector. Now please observe, we have a input X and we have a output Y. We have a input X and we have a output Y. So now please observe here, what is the sequence of the input onto the sequence detector? Sequence detector receives a particular message. And if we observe, the message is 101, 1010, 11. Is it okay? Yes, sir. And output will become logic 1 only when the required set of sequence got detected. Only when the required set of sequence got detected. Yes, sir. So now please observe, when first bit received at the input to the sequence detector and a clock is applied, one bit is received but the entire sequence is not get detected, so output is 0. Second bit is also received as 0, but still we will receive the output 0 because entire set of sequence 1010 is not got detected. Next bit 1 received at the input and on the next clock pulse even we have output 0. Next bit 0 received at the input. Now the sequence got detected. This is the required sequence got detected. So on the fourth clock pulse, we are getting the required sequence got detected. 1010. The entire 4 bit in a sequence got detected. So output will become logic 1. So output will logic 1 only when the required set of sequence got detected in case of a sequence detector circuit. Hoping all of you have now overview of the sequence detector. Great. Beta ji, please let me know by writing in the comment section. All of you have now an overview of the sequence detector. Great, sir. Very important. Please observe. If we talk about sequence detectors, then sequence detectors can be a non-overlapping sequence detectors or a overlapping sequence detector. Overlapping sequence detector can be 1 bit, 2 bit, 3 bit, 4 bit, and so on. Is it okay? Non-overlapping sequence detector is one in which the bit once detected is not reused for counting the sequence or the term of sequence. Okay? Yes, sir. Let's try to understand with the help of question. First, observe non-overlapping sequence detector. When we talk about non-overlapping sequence detector, so non-overlapping sequence detector is one which detects the output with the input sequence non-overlapping. So we have a X as the input and Y as the output of the sequence detector, input and output, and we have one bit sequence detector. We have sequence detector to detect sequence 1101. Suppose I want to detect a sequence 1101. I want to detect a sequence 1101. So in a clocked synchronous sequential circuit, we are giving input bit streams onto the X and we are getting output onto the Y. Output Y will become logic 1 only when the input bit stream follows the given sequence. Is it okay? And that too non-overlapping. We have to identify whether 1010 in a 1010 sequence detector, if we got received this message at the input X and this message is received in a sequence from left to right. So in a sequence from left to right. Is it okay? Now please observe what happens to output Y. Please observe, we have to we are designing 1101 sequence detector. So for one it will remain low, 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 high. Why? Because 1101 got detected. Then again it is a non-overlapping. So non-overlapping means next sequence get started from here. Is it okay? Next sequence got started from here. So 1101. So again 000 sequence got detected. Again 11. Let us suppose if we have instead of 11, suppose if we have this, then your output will remain low only. Why? Because the required set of sequence not got detected. The output will become logic 1 only when the required set of sequence got detected. In a non-overlapping case, this one is not considered. This one is not considered. Is it okay? How many of you able to understand this? Let me modify it further. We have to design 1101. So we are getting 1101 But in a 1101, this one bit got overlapped. The last bit of the previous sequence can't be the first bit of the next sequence in a non-overlapping sequence detector. In a non-overlapping sequence detector. So what we are getting 0, 0, 0 only. Is it okay? For the last 4 bits, we are getting 0, 0, 0 only. How many of you now able to understand a non-overlapping sequence detector? Great. Now you know about the overlapping sequence detector as well. So we have a 1-bit overlapping sequence detector. Let's talk about 1-bit overlapping sequence detector. If we have a sequence detector with the input X, output Y, input X, output Y in a clocked synchronous sequential circuit to detect sequence of input with stream 1101. If we want to detect 1101, please observe here, Betaji. I need your response. Please observe here. Now, when your output will become high, whenever the required set of sequence got detected, 1101, yes, sir. So here your output will become high onto the 4th clock because the required set of sequence got detected. Sequence is from left to right. Okay. Next, if you observe, it is a 1-bit overlap. So this it will start from here. Is it okay? This will start from here. The last bit of the previous sequence will become most significant bit of the next sequence. Is it okay? This is a 1-bit overlap. So here we are getting 1-bit overlap. 1-bit overlap. How many of you able to understand? Great, sir. So the output will become 0, 0, 1 because the required set of sequence got detected. Again, please observe, it is a 1-bit overlap. So 1101, 1101, it indicates again the output will become high. How many of you now able to understand the 1-bit overlap? If you know 1-bit overlap, you know 2-bit overlap as well. What is 2-bit overlap? The last 2-bit of the last sequence detected will become first 2-bit of the next sequence. That will become a 2-bit overlap. Is it okay? Yes, sir. Let's have a discussion on to the 2-bit overlap. So please observe here. What happens in case of a 2-bit overlap? I'm changing this little bit, okay? Or keep it as it is. Suppose if we want to design a 2-bit overlap, 1101. Okay, let me modify it a little bit. One zero zero one and okay. Can you now tell me what will be your output Y? Again, we have a sequence detector. Now we have a 2-bit overlap sequence detector. Now we have a 2-bit overlap sequence detector to detect sequence 11001. Okay, we are getting the input X onto the input port. Your output port will become high in a clocked synchronous sequential circuit only when the input sequence got detected 11001. So if you observe here, we have 11001. So 11001 sequence got detected. It's a 2-bit overlap. It's a 2-bit overlap. So what is the meaning of 2-bit overlap? 2-bit overlap means it can be taken from here or it can be taken from here, but we can't take from here. Why? Because the required set of sequence is not available. Is it okay? Yes, sir. So now if you observe a 2-bit overlap, 0 1 0 1, it is never going to be a 2-bit overlap, na? Okay, I'm sorry, beta ji. Actually, I made such arrangement that never goes to 2-bit overlap. 2-bit overlap, this must be 0. So I am converting it to 0 1 0 0 1. Okay, 0 1 0 0 1, 0 1 0 0 1, 0 1 0 0 1. Let me rearrange this. 0 1 0 0 1, 0 1 0 0 1, 0 1 0 0 1, 0 1 0 0 1. Okay. Suppose if this is the input bit stream in a 2-bit overlap, suppose this will be the input bit stream. Okay. So in a 2-bit overlap, if we talk about 2-bit overlap, if this is the input bit stream and the output will become logic 1 only when the required set of sequence got detected. So all of you can observe here 0 1 0 0 1, 0 1 0 0 1 is the required set of sequence, 0 1 0 0 1 is the required set of sequence, so output will become logic 1. It's a 2-bit overlap. 2-bit overlap means last 2-bit of the previous will become first 2-bit of the next sequence. So what you will get? 0 1 0 0 1, 0 1 0 0 1, 0 1 0 0 1. So required set of sequence got detected. Again, if you observe, it's a 2-bit overlap. So 0 1 0 0 1. How many of you able to understand up to the part of 2-bit overlap, beta ji? Please let me know by writing in the comment section. 0 1 0 0 1. So how many of you able to understand this 2-bit overlap now? Please let me know by writing in the comment section, beta ji. Someone has made a comment and then again removed. What happened, beta? Why you are removing your comment? Is there any issue? Anything that you are unable to understand, please let me know by writing in the comment section, beta ji. Understood? Great. So now we know about the overlapped 2-bit, 1-bit, 3 bits and n number of bits overlap in any digital message, as the output will become logic 1 only when the required set of input sequence got detected. Is it okay? Yes, sir. Now please observe here. Very important point while designing, one must note very important point while designing the sequence detector. Okay. See, if we have to design a n-bit sequence detector, if we have to design a n-bit sequence detector, if we have to design a n-bit sequence detector, then number of states required in a Mealy machine, number of states required in a Mealy machine is equals to n. N is the number of bits. Suppose we are interested here to design 1, 2, 3, 4, 5 bit. 5 bit? It's a 5-bit sequence detector circuit. For a 5-bit sequence detector circuit, if you want to design a 5-bit sequence detector circuit, then Mealy machine required 5-bit. Is it okay? Yes, sir. And number of states in a Mealy machine will become 5. However, for a 5-bit sequence detector, Moore model requires number of states n plus 1. So for a 5-bit required 5 plus 1, that is 6 states are needed. So always remember, number of states needed in Mealy model is less comparative to number of states needed in Moore model. many times already asked in the previous PSUs as well as engineering services. So always remember this. Number of states required for a Mealy model, number of states required for a Mealy model is always less than number of states required for a Moore model. Number of states required in a Mealy model is equals to number of bits, and Moore model it is number of bits plus 1. Is it okay? Yes, sir. Now, one very important point, m is less than or equals to 2 to the power n, where m is the number of states and n is the number of flip-flops. Okay? Yes, sir. So suppose if we have a 4-bit sequence detector, then a 4-bit sequence detector through Mealy model required only 2 flip-flops. However, a 4-bit sequence detector by using Moore model required 5 states, and 5 states means it required 3 flip-flops. Is it okay? So it can be clearly observed that there is a possibility of Moore model having higher cost comparative to Mealy model. Is it okay? Yes, sir. Now please observe how to design any sequence detector by using Mealy model. How to design sequence detector by using Mealy model. Is it okay? Yes, sir. How to design sequence detector by using Mealy model? In a Mealy model, first point, non-overlapping Mealy model, you have to take first state as a reset state and move the last bit when sequence got detected to the reset state. Just note down, it's a process that we will follow. Next is, in a 1-bit overlapping, compare the last bit with the 1-bit state. If it matches, then you can say you will end your state diagram at 1-bit state. Otherwise, you will go back to the reset state. In case of a 2-bit state, compare the last bit when sequence got detected to the 2-bit state. If it does not matches, then compare last 1 bit with the 1-bit state. If that also not matches, then only you will go to the reset state when your entire state diagram completes. Is it okay? Yes, sir. And the same process goes on for the 3-bit and so on. Is it okay? Yes, sir. Now please observe, we are interested to design. I am going to show this again and again. Okay, but let us first move towards the non-overlapping Mealy model. Okay, so non-overlapping Mealy model. Let's try to understand with the help of one question. Suppose we have to draw a sequence detector by using Mealy model. So how we can design a sequence detector by using Mealy model? How we can design a sequence detector by using Mealy model? Is it okay? Yes, sir. Please observe, beta ji. First, draw the state. I am considering it as a question, so please make it like a question. Draw a state diagram for the sequence detector for the non-overlapping sequence detector, non-overlapping sequence detector to detect sequence, whatever sequence you want. You can just tell me in the comment section, any 4-digit, any 4-bit. You can just tell me any 4-bit, 1001, 1101, 100, anything, whatever you want. You can design any sequence detector. Is it okay? So let's take 1, 0, 0, 1. Suppose you want to design, if you want, you can just tell me in the comment section. I will take that. If anyone wants to design their own sequence detector, just let me know in the comment section what particular sequence detector you want to design. That I am going to design. Please let me know by writing in the comment section. Hi Aditya. Just write down in the comment section whatever sequence detector you want to design, but keep it in only 4-bit, okay? The purpose is because I don't want to exceed more than one board, okay? So just take it up to the 4-bit, okay? Great. So I am considering 1001 as I am not getting any response in the comment, so I am taking 1001. Suppose we want to design a non-overlapping sequence detector to detect a sequence 1001. So how to design it? Please observe here. First of all, how many number of bits are there? How many number of bits are there? Number of bits is equals to number of states. Number of states in Mealy model is equals to number of bits. So that is equals to 4. So we have to use 4 states. I am assigning the name to do these 4 states. Let us suppose these 4 states are state A, state B, state C, and state D. So I am assigning name to these 4 states as A, B, C, D. Is it okay? Yes, sir. How many number of flip-flops are required to design such a Mealy model? Only 2 flip-flops are required. Because we have 4 states, so m is less than or equals to 2 to the power n. You know that n is equals to 2. Only 2 flip-flops, 0, 0, 0, 1, 1, 0, 1, 1. 4 states can easily be designed. Now please observe here. If you are on state A, there are 2 possibility of input got received. Maybe the input received to the sequence detector is 0, or maybe the input received onto the sequence detector is logic level 1. This is your sequence detector. X is the input, Y is the output. Yes, sir, we have this. We want to design a sequence detector. So, in this particular circuit, the input X can be 0 or 1. If you are on state A, first we take one state as a reset state. So, one state we must have to take reset state. It means 0, 0 state is a reset state, okay? So if you are on reset state and if X is equals to 0 received, then it is not the part of the required set of sequence. So it means if 0 received, you will remain in reset state and output will remain 0. Output will become logic 1 only when the required set of sequence got detected. Is it okay? Yes, sir. If you are on state A, and input X is equals to 1 received at the input X of the sequence detector, then it means it is the part of required set of sequence. So you have to move from state A to state B. Is it okay? So when input 1 is received, you have moved to state B because 1 is the required bit of the input required in a required sequence detector. However, the output will remain 0 because entire set of sequence not yet got detected. This particular B is a 1-bit state. What is the meaning of 1-bit state? Actually, this 1-bit state means 1 bit is got detected. This is your 1-bit state. 1-bit state means 1 bit is already detected, then only you have reached to state B. So 1 bit of the required sequences got detected, then only you have reached to state B. Is it okay? Now, if you are on state B, it means 1 bit is already detected. 1 bit is already detected of the required sequence. Next input bit, next time the input X can be 0 or 1. Yes, sir. 1 is already detected. This 1 is already detected. Next input bit can be 0 or 1. If you are getting 0, then it is a required set of sequence. So you will move to next state and output will remain 0. However, if you are getting 1, then this is not the required set of sequence. Under such a condition, you have to compare this last 1 bit with a 1 bit state if it matches B in a state B. Otherwise, go back to reset state. So since 1 bit, last 1 bit is matches with the 1 bit state, so remain in state B. So if we are getting 1, we will remain in state B. However, if we are getting 0, we will move to the next state. Now, when you are on state C, it indicates already 2 bits of the sequence got detected. 1, 0. These 2 bits in a sequence got detected. Then only you have reached to 2-bit state. So 2 bits are already detected. If 2 bits are already detected, now the third input bit onto the X can be 0 or 1. 2 bits are already detected. Yes, sir, 2 bits are already detected. Now, third bit can be 0 and 1. If it is 0, it means 0 is the required set of input sequence. So, you will move to state D. Output will remain 0 because entire set of sequence not yet got detected. However, if you are getting 1, then this is not the required set of sequence. In such a case, you have to compare the last 2 bit with a 2-bit state. If it matches, compare the last 2 bit with a 2-bit state. This is not the last 2 bit. I'm sorry, beta. This is the last 2 bit. Okay. Compare the last 2 bit. Compare the last 2 bit. I'm talking about this. Compare the last 2 bit. This 0, 1. Compare the last 2 bit with a 2-bit state. If it matches, remain in state C. If it does not matches, compare the last 1 bit with a 1-bit state. If it matches, go back to that state. If that does not matches, go back to the reset state. So since it is matching, the last bit is matching with the 1-bit state. So go back to the 1-bit state. If you receive 1, output will remain 0 because entire set of sequence not yet got detected. Now come to the state D. You have reached to state D. It means 3 bits in a sequence already got detected. You have reached to state D. It means 3 bit in a sequence already got detected at input X. Now next input at X can be 0 or 1. Yes, sir. Next input on X can be 0 or 1. Only 2 possibility with the 1 input. Yes, sir. If we are getting 0, then this is not the required set of input sequence. Now compare the last 3 bit. Compare the last 3 bit with a 3-bit state. If it matches, remain in state D. Otherwise, compare the last 2 bit with a 2-bit state. If it matches, go back to state C. Otherwise, compare the last 1 bit with a 1-bit state. If it matches, go back to state D. If it does not matches, then go back to the reset state. So since the last is not matching, so go back to the reset state, that is the state A. 0, 0, because required set of sequence is not got detected. However, if we have next bit is 1, then this is the required set of input sequence. When the required set of input sequence got detected, move the last bit when sequence is detected to 1-bit state or reset state. It means in a non-overlapping, when entire sequence got detected, move to the reset state. So we will move to the reset state. Here the output will become logic 1. Why? Because the entire set of sequence got detected. Output will become logic 1 only when the required set of input sequence got detected. How many of you able to understand? Sir, can't understand. Why, beta? Why you are not able to understand? Okay, let me show you once again. We want to design a sequence detector. We want to design a sequence detector. Please observe once again. I am repeating once again with the help of one question. We want to design a non-overlapping sequence detector. We want to design a non-overlapping sequence detector. Okay. So, state diagram for non-overlapping one-bit non-overlapping sequence detector detector to detect sequence. Okay, tell me, please tell me any four bit combination. 1001, 0110, 1110, anything. Whatever you want, please tell me. So we want to design a 1-bit non-overlapping sequence detector. We want to design a 1-bit non-overlapping sequence detector to detect sequence. Please tell me any 4-bit. Okay, any desired 4-bit. Okay, by using Mealy model. Okay, yes sir. See, sequence detector is a sequential circuit in which we receive the input at X, input bit stream at X, and we have a output Y. Output Y will become logic 1 only when the required set of sequence got detected, and we have a clock. So this is a required sequence detector. Actually, we are interested to design the digital circuitry inside this box. To design the digital circuitry inside this box, first of all, we need to draw the state diagram. From the state diagram, we can construct a state table. From the state table, we can construct excitation table. Then we can find the excitation equation and minimize it, implement the logic circuit. So we will be able to design the circuit inside of this detector required. Is it okay? Someone is saying, okay, sir, 0, 1, 1, 0, or Aditya is saying, sir, 1, 0, 1, 0. So let's take 0, 1, 1, 0. Okay, you can take any. So I'm just considering 0, 1, 1, 0. See, it's a non-overlapping. Very important term is it's a non-overlapping. Is it okay? Yes, sir. Now please observe. First of all, please let me know by writing in the comment section how many number of states required if we want to design by using Mealy model. Number of states required for a sequence detector by Mealy model is equals to number of bits. Number of states in a Mealy model is equals to number of bits. How many number of bits are there? 1, 2, 3, 4. 4 bits. So how many number of states? 4 states. For 4 states, we require 2 flip-flops. 0, 0, 0, 1, 1, 0, 1, 1. Very simple. Yes, sir. So I'm just assigning name to the states. States are 0, 0, 0, 1, 1, 1, 1, 0. So I'm assigning name to those states as A, as state A. This is 0, 0 state, state B. You can say 0, 1 state, state C, 1, 0 state, and you can also say state D as 1, 1 state. It's up to you. Any 4 different states just you have to see. Is it okay? Yes, sir. Now please observe. Suppose you are on state A. If you are on state A, first observe what is the required set of sequence. So if you are on state A, always remember the first state A is a reset state. Reset state means a 0, 0 state. Is it okay? Yes, sir. So suppose if this we are getting at the input. So if we receive 0 on X, first if we receive 0 at the input X, then if you are on state A, you will move to state B. Output will remain low. This is the input, this is the output, this is the present state. If you are in present state A, you have given the input 0, you will move to state B and output will become 0. Is it okay? Yes, sir. Output will be high only when the entire sequence got detected. So we have only 1 bit got detected. Next, if you are on B and next bit onto the X received as 1. First you received 0 and now you are receiving input X is equals to 1. Then if you are in state B, you will move to state C and output will remain 0. If you are on state C and next bit 1 is received, you will move to state D and output 0. If you are on state D and input X is equals to 0 received, then you will go back to the reset state and output will become logic level 1 because entire set of sequence got detected. Is it okay? Yes, sir. Now please observe. Now please observe. If you are on state A, there are two possibilities. Maybe the input received at X is a 0, or maybe the input received at X is logic level 1. So if logic level 1 will receive, that is not the required set of input sequence, under that condition you will remain in state A only, and output is 0. If you are at state B, it indicates one bit is already detected. If you are on state B, it means one bit is already detected. If you are on state C, it means 1, 0, 2 bits are already detected. If you are on state D, it means 3 bits are already detected. So I am calling state B as a 1 bit state, state C as a 2 bit state, and state 3 as a state D as a 3 bit state. What does it mean? It means if you are on state A, none of the bit is got detected of the sequence. If you are on state B, it means one input bit of a sequence got detected. If you are on state C, it means 2 input bits are being detected in a sequence. If you are on state D, it means 3 input bits are being detected in the sequence. Now please observe, if you are on state A, X is equals to 1 appear, you will remain in state A, output is 0. If you are on state A, input X is equals to 0, you will move to state B and output will be 0. It means one bit is received, and what is the bit? 0. Now one bit is received. Next bit on the input X can be 0 or 1. Is it okay? Yes, sir. One bit is already received. One bit is already received. If you are getting 0, then this is not the required set of input sequence, because we need 0, 1. We don't need 0, 0. So this is not the required set of sequence. In such a case, you have to compare the last one bit with the one bit state. If it matches, remain in the same state. Otherwise, go back to the reset state. So since it matches, so you have to remain in this state if you receive 0. Is it okay? Output will remain 0. However, if you receive 1, it means 0, 1. 0, 1 is the required set of input pattern. So you will move to state C. Output is still 0 because entire set of sequence not yet got detected. If you reach a C, it means this 0 and 1, 2 bits are being received. 0 and 1, 2 bits in a sequence got received. Then only you have reached to state C. Now, next third bit onto the input X can be 0 or 1. Is it okay? 2 bits are already we have detected in a sequence. Now this third bit, which I have represented by the green symbol, onto the X can be 0 or 1. If we are getting 0, then this is not the required set of input sequence, because we want 0, 1, 1, 0. So this is not the required set of sequence. 0, 1, 0, this is not the required set of sequence. Under such a condition, either it will remain in state C or it go back to the previous states. That we can check with the last 2 bit. Compare the last 2 bit with the 2 bit state. If it matches, remain in state C. Otherwise, compare the last 1 bit with the 1 bit state. If it matches, go back to that state. So since it is matching, so go back to next state, because we are getting 0. On 0 we are not getting the required set of sequence. So I have compared the last 1 bit with the 1 bit state. It matches, so go back to that state. If it does not matches, you have to go back to the reset state. Is it okay? Now, if we are getting 1, this is the required set of input sequence pattern. So 0, 1, 1 is the required set of sequence. So now move to the state D if you are getting 1. So if you are getting 1, if you are on state C and you are getting 1, move to the next state D. Now 3 bits in a sequence got detected. Your 4th bit onto the input can be 0 or 1. 3 bits in a sequence already got detected. 3 bits in a sequence already got detected, that I have represented yellow. Green, the next bit X can be 0 or 1. If we are getting 0, what happened? If we are getting 0, then this is the required set of input pattern. You will reach to reset state in case of a non-overlapping, and output will become logic 1 since the entire set of sequence got detected. Is it okay? Yes, sir. So whenever move the last bit when sequence got detected to the reset state in case of a non-overlapping Mealy model. Is it okay? Yes, sir. However, if we are getting 1, so this 1, it means 0 triple 1. 0 triple 1 is not the required set of sequence. So what happened? We have to compare the last 3 bit with the 3 bit state. If it matches, remain in state D. Otherwise, compare the last 2 bit with the 2 bit state. If it matches, go back to 2 bit state. Otherwise, compare the last 1 bit with the 1 bit state. If it matches, go back to that state. Else, you have to go back to the reset state. So since it is not matching to any, so go back to the reset state. So if we are getting 1, then we will go to the reset state. Sequence not got detected, so output is 0. Output is logic 1 only when the sequence got detected. How many of you now able to understand the non-overlapping, how to design the state model of a non-overlapping sequence detector? Is it okay now? Great, sir. Any doubt? No, sir. Very good. Now come to the 1 bit overlapping. Let's talk about 1 bit overlapping. So 1 bit overlapping, draw a state diagram for the sequence detector. 1 bit overlapping Mealy model. Mealy model for sequence 1101. So can you design for 1101? Beta ji, please see. How many number of states are there? 4 states are there. So in case of a Mealy model, how many number of states are there? 4 states. How many number of flip-flops needed? 2 flip-flops are needed for 4 state. Okay, great. So I am giving the names to those 4 states. So we have a state, let us suppose A, we have a state B, we have a state C, and we have a state D. Is it okay? Yes, sir. We want to design a sequence detector where the input bit stream is onto the X and output will become high only when the required set of sequence got detected on the sequential circuit. So which sequence we want to detect? Sequence detector 1101. We want to design a sequence detector 1101. Now please observe, same thing goes on. If you are on a state A, 2 possibility of the input to X, maybe 0, maybe 1. If you are getting 1, you will reach to the next state. Otherwise, output will remain 0 because unless the sequence got detected, output will remain 0. If you are on a state A, instead of X is equals to 1, if we get X is equals to 0, then this first is a reset state. So reset state, you will remain in the reset state. If you are getting first bit 0, output is not got detected, so output will remain 0. Now if you are on state B, it means 1 bit is already being detected. X can now be 0 or 1. If you are getting X, if you are getting X 0, then this is not the required set of input pattern. You have to compare this 0 with this 1 bit, this last bit with the 1 bit state. If it matches, B on state B, remain on state B. Otherwise, you have to go back to the reset state. Output remain low. If we are getting X is equals to 1 and we are on state B, then you will move to state C because this is the required set of input sequence. Output will remain low because entire sequence is not yet got detected. Now we have reached to 2-bit state. If you are on state C, it means 2-bit in a sequence already got detected. Now X will again have 2 possibilities, 0 or 1. 2 bits are already detected in the sequence. If you are getting 0, this is the required set of input pattern. You will move to the next state, output will remain low because entire set of sequence not yet got detected. However, if you are getting 1, compare the last 2 bit, because this is not the required set of sequence. So compare the last 2 bit with the 2 bit state. If it matches, remain in this state. Otherwise, you have to compare the last 1 bit with the 1 bit state. If that matches, go there. Otherwise, you have to go to the reset state. So since this last 2 bit is matching with these 2 bit states, so remain in this state. Output will remain 0 because entire set of sequence not yet got detected. If you observe state D, if you have reached to state D, it means already 3 bits in a sequence got detected. Now X, input X onto the sequence detector may be 0 or 1. If we are getting 0, then what does it mean? It means this is not the required set of input sequence. Under such a condition, you have to compare the last 3 bit with the 3 bit state. If it matches, remain in state D. Otherwise, compare the last 2 bit with the 2 bit state. If it matches, go back to the state C. Otherwise, compare the last 1 bit with the 1 bit state. If it matches, come back to the state B. Else, you have to go back to the reset state. So since nothing is matching, so you have to go back to the reset state. Output will remain 0 because entire set of sequence not yet got detected. If you observe here, already we are getting these, and if we get 1 at the input X, entire set of sequence got detected. In case of a 1 bit overlap, please observe here. In case of a 1 bit overlap, you have to compare the last bit when sequence got detected to 1 bit state. Your state diagram may ends at 1 bit state if the last bit matches with a 1 bit state. So if you observe here, because it's a 1 bit overlapping, we are here, yes, because it's a 1 bit overlapping. So when all the sequence got detected, entire sequence got detected, yes sir, entire sequence got detected. Now you have to compare the last bit with the 1 bit state. So it is matching with the 1 bit state, yes sir. So you have end your state diagram here. If we are getting 1, output logic 1 because entire set of sequence got detected. So this will be the state diagram of your required 1 bit overlapping Mealy model. How many of you able to understand now? Great. How many of you able to understand now? Great. Now please observe 2 bit overlap. Now please observe the last one, that is 2 bit overlap. In case of a 2 bit overlap Mealy model, we are talking for a Mealy model, okay? So 2 bit overlap Mealy model. If we talk about 2 bit overlap Mealy model, let us suppose we have a sequence 11011, mostly used in many of the books. So 11011. State diagram for the sequence 11011. So if we have to design a state diagram for the sequence 11011, so please observe how many number of bits are there? 1, 2, 3, 4, 5. So how many number of states required? Number of states required in case of a Mealy model is equals to number of bits. So we need 5 state. 5 state, let them given a name as A, B, C, D, E. Okay. Yes, sir. So I am giving the states name as A, state B, state C, state D, state E. Okay. Yes, sir. Now if you are on state A, if you are getting 1, you will move to the next state. If you are getting 0, you will remain in state reset state. First one is a reset state. This is your reset state. Reset state means 0, 0, 0. Is it okay? Yes, sir. So 5 states definitely we have. 5 states possible. It means 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Maybe we have 5 different states. Okay. Or binary of 0 to binary of 4. Maybe have 5 different states. Is it okay? Yes, sir. So we have 0, 0, 0 is a reset state. If we are getting 1, that is the first bit of the sequence, we will move to the next state. Otherwise, we'll remain in the same state. State B is a 1 bit state. State C is a 2 bit state. State D is a 3 bit state. And state CE is a 4 bit state. It means if you are on state B, 1 bit is already detected in a sequence, 2 bits are detected in a sequence if you are on a state C, 3 bits are in the sequence if you are on a state D and 4 bits are in the sequence if you are on state E. Is it okay? Yes, sir. Now please observe here. If you are on state B now, it means already one input is detected. So this 1 bit, you have got 1 bit detected already. Now, if again next you get 1, you will move towards state C. And if you get 0, then if you are getting 1, you will move ahead. If you are getting 1, you will move ahead. But if you are getting 0, then if you are getting 1, you will move ahead. Okay, yes sir. But if you are getting 0, then you have to compare the last bit with the 1 bit state. Last bit with the 1 bit state. If it matches, remain on state. Go back to state B. Otherwise, if you are on state B and if 1 is received, you will move to state C. If you receive 0, then you have to check 1 bit state. If it matches, remain in state B. Otherwise, go back to the state A. So for 0, you will go back to the state A. Now, if you have reaches here, it means 2 bits are already being detected. So 2 bits are already being detected. Next bit on the input of the sequence detector may be 0, may be 1. If you are getting 0, you will move to the next state. Output will remain 0. If you are getting 1, compare the last 2 bit with the 2 bit state. If it matches, remain in this state. How many of you able to understand? Otherwise, you have to compare the last 1 bit with the 1 bit state and then go back to the reset state. Now, if we are on 3 bit state, state D, it means 3 bits are already being detected in the sequence. 3 bits are already being detected in the sequence. Now your X input can be 0 or 1. Already 3 bits are detected in a sequence. So if you are getting this, you will move to the next state. No. If you are getting 0, you have to compare the last 3 bit with the 3 bit state. If it does not matches, compare the last 2 bit with the 2 bit state. If it does not matches, compare the last 1 bit with the 1 bit state. Otherwise, go back to the reset state. So they are not matching, so go back to the reset state. Output will remain 0 unless the entire set of sequence got detected. If you observe now, we are getting 1, then this is the required set of sequence 1101. Yes sir. So you will move ahead towards the next state. Output will remain 0 because entire set of sequence not yet got detected. Now we have 4 bits already detected. 5th bit maybe 0, maybe 1 coming onto the sequence detector. If we are getting this, so this is not the required set of sequence. Compare the last 4 bit with the 4 bit state. If it matches, remain in state E. Otherwise, compare the last 3 bit with the 3 bit state. If it matches, go back to state D. Otherwise, compare the last 2 bit with the 2 bit state. If it matches, go back to state C. Otherwise, compare the last 1 bit with the 1 bit state. If it matches, go back to the state B. Otherwise, go back to the reset state. So none of the states are matching. So you will have to go back to the reset state in case of 0. However, if you are getting 1, then this is the required set of sequence. For the required set of sequence, in case of 2 bit overlap, when the entire set of sequence got detected, compare the last 2 bit with the 2 bit state. If it matches, end at that particular state. Is it okay? Yes sir. So compare the last 2 bit with the 2 bit state. So it is matching in case of 2 bit overlapping. Yes sir. So it will be ended to state 2 bit state. 2 bit state is your state C. So if we are getting 1, it will reaches to state C. Output will become high because entire set of sequence got detected. How many of you able to understand how to draw the 2 bit overlap, 1 bit overlap or non-overlapping sequence detector state diagram? Hoping all of you able to understand this. Yes sir. Now let's try to draw one sequence. Let's try to design one sequence detector. Okay, let's try to design one sequence detector. In objective exams, they will give you this state diagram and ask you what is the sequence we are detecting from the state diagram of a state machine or a sequence detector shown below, and whether it is a 1 bit overlap, 2 bit overlap or non-overlapping. So you can easily observe with the ending, and there is only one position where you are getting output logic 1, and by observing that you can conclude whether it is a overlapping, non-overlapping 1 bit or 2 bit overlapping. And also you can detect the sequence. What is the sequence detector here? We have a sequence detector 1, 1, 0, 1, 1, 1, 0, 1, 1. How many of you can observe the sequence detected by this sequence detector is 1, it means it goes to next state, 1 no goes to next state, 0 goes to next state, 1 goes to next state, 1 goes to end up. So it is a 2-bit overlap sequence detector to detect a sequence double 1, double 1, 0, double 1. Is it okay? So this kind of question they may ask you. Already they have designed such kind of questions in PYQs. Is it okay? Previous years. Now let's try to design one sequence detector by using Mealy model. Let's try to design one sequence detector by using Mealy model. And I am going to give you the opportunity to you to decide what sequence detector you want to design. Okay. First, if we want to design a sequence detector by using Mealy or a Murray model, we have to follow the certain set of steps. So if you observe here, step 1 indicates, first of all, find the number of states in a state diagram. Find the number of states in a state diagram. Find the number of states in a state diagram equal to the number of states in a state diagram is equals to number of bits in a sequence for Mealy model and n plus 1 states in Murray model. Is it okay? Number of states required in a state diagram is equals to number of bits in a sequence for Mealy model and number of bits in a sequence plus 1 number of bits in a sequence plus 1 in Murray model. Number of bits in a sequence plus 1 in Murray model. Is it okay? Yes, sir. Where n is the number of bits. Number of bits are n. Capital N is representing number of bits. Okay. Yes, sir. Next, draw the line directions between the state input and output. Draw the line directions between the state of input and output. Is it okay? Third, state assignment and construction of state table. We have to assign the states and then construct state table. Fourth step is to draw the excitation table from the state table. Draw the excitation table from state table. Whatever state table we have constructed, we will utilize that state table to draw the excitation table. Then step 5, use K-map for simplification of excitation equation. Excitation equations. Okay. Yes, sir. And sixth, implement the logic circuit. So only we have to follow these 5 steps. Sixth step is the implementation of circuit only. Is it okay? Let's try to understand all these steps once again, and we will see how we can design any desired sequence detector. So what kind of questions are possible? They may ask you to design a sequence detector and they will give in the options circuitry you have to identify. They may ask you the input of the sequence detector design. Okay, any one of the input of the sequence detector design, or they may ask you to design the state table from the given sequential circuit. Is it okay? They may give you a state diagram to ask reduce the state table, reduce the state diagram, anything. Okay. They may give you a state diagram and ask you to identify the sequence detected by the sequence detector shown below, in that way also. Okay. Let's try to understand with the help of one question. I am giving you opportunity to decide any 4-bit. Okay. So design, I am going to design only one, and that one circuit will help you to design any desired. So design a non-overlapping sequence detector to detect a sequence by using Mealy machine. Use JK flip-flop. use JK flip-flop. There is no boundation of the flip-flops. We will decide the flip-flop which will have the lowest delay. Along with the flip-flop, the logic gates required will be minimum. That we will choose. Okay. So please let me know any 4-bit sequence. I am using 4-bit because otherwise it will become very the big circuit. Okay. So lot of calculations are going on. So just let me know any 4-bit, whatever you want to design. Any 4-bit sequence detector, whatever you want to design. Okay. So let anyone want to have the choice? Please put your choice in the comment section, Betaji. So now we are going to design your desired sequence detector. Please let me know any 4-bit. Whatever sequence detector you want to design, just let me know. Suppose, since none of you have given any choice, so let's take this sequence detector. Okay. So 0, 1, 0, 1, 1. We want to design 1, 0, 1, 1. So how many number of states are there? Now please observe, I am solving this question properly. Please observe. So n number of bits in sequence is equals to 4. So number of states in Mealy model is equals to n, that is equals to 4. So for 4 states we have 4 variables. Next is state assignment and construct state table. Is it okay? Yes, sir. So I want to design a sequence detector with the input X, output Y, okay, and clock sequence detector for sequence 1, 0, 1, 1 to detect a sequence 1, 0, 1, 1. Okay. Yes, sir. Let us suppose you have said to me, sir, I am going to send you a message in a coded form. So for that you can just design one decoder, and while designing your decoder you can use this 1, 0, 1, 1. This 1, 0, 1, 1 is a decoder of my message. So I will send a bit of streams with the other inputs as well in the streams. Outputs are becoming high only in a set pattern, and that can be, we can decode the message. Is it okay? So no one else know what message we have sent it, only the decoder and the sender knows what message is called. Is it okay? Great, sir. So we are interested to have 1, 0, 1, 1 sequence detector circuit. Please observe here. For that, first of all, we have to use a state assignment. So state assignment, total number of states required will be 4. So 4 states, let states A will be your state 0, 0, reset state B 0, 1, state C 1, 0, and state D 1, 1. So I am assigning the different states in a Mealy model. So we want to design a 4-state Mealy model. Is it okay? So I am naming the states as A, B, C, D. Number of flip-flops required will be equals to, sir, for 4 state, number of flip-flop required will be equals to 2 only. So 2 JK flip-flop needed. So in this circuit, we need 2 JK flip-flop. Is it okay? Yes, sir. Next is to construct a state diagram. Okay. Yes, sir. In a state diagram, we have a state A, state B, state C, and state D. Is it okay? We all know how to use the how to draw the state diagram. State A is always a reset state. So if we are getting the input 1, if we are getting the first input 1, then for a first input 1, we will reach to the next state. If we are getting 0, we will remain on to the same state, output is 0. If you are on state B, it means one bit in a sequence already got detected. One bit in a sequence already got detected. One bit in a sequence already got detected. Now, if the next bit is 0, then this is the required set of input. You will reach to the next state, output 0. If you are getting 1, then compare the last 1 bit with the 1 bit state. If it matches, remain in the same state. Else you have to go back to the reset state. Now if you are on a state C, it means already 2 bits in a sequence got detected. Now next can be 0 or 1, x can be 0 or 1. If we are getting 1 0 0, this is not the required set of sequence. You have to compare the last 2 bit with the 2 bit state, last 1 bit with the 1 bit state. Since they are not matching, so go back to the reset state. If we are getting 1, this is the required set of input pattern. So move ahead, output will remain 0 because entire set of sequence is not yet got detected. If you are in a state D, it means already 3 bits in a sequence got detected. 3 bits in a sequence got detected. Now fourth bit can be 0 or 1. If you are getting 0, this is not the required set of input pattern. So you have to compare the last 3 bit with the 3 bit state, then last 2 bit with the 2 bit state. Since it matches with the last 2 bit, so go back to the 2 bit state. In case of 0, output will remain 0 because the entire set of sequence not yet got detected. However, if you are getting 1, the entire set of sequence 1 0 1 1, 1 0 1 1 is the required set of input sequence. So when it detected, you will go back to the reset state in case of a non-overlapping. Output will become logic 1. Why? Because entire set of sequence got detected. So this is how we can construct the state diagram. Now from the state diagram, we can now construct a state table. How many of you able to understand up to this part? Beta ji, I need your response. Next is to construct your state table. Yes, sir. So I'm using state table. State table, we have a state table. So in a state table, we have present state, present state, next state. Since we have only one input x, so there are two possibility of x is equals to 0 or 1. In case of two inputs, we may have four possibility x is equals to 0 0, xy 0 0, xy 0 1. In case of 3, we have 6 possibility and so on. So presently we have only one bit. So one input bit. So for one input bit, we have only one possibility of x is equals to 0 or x equals to 1. Is it okay? Yes, sir. Then we have output with x is equals to 0 and x is equals to 1 because we want to design a Mealy model. In a Mealy model, output is the function of input as well. So if we talk about present state, then present state is, sir, we have a present state 0 0, 0 1, 1 0 or 1 1, which can be represented in terms of variables state A, state B, state C or state D. Is it okay? Yes, sir. Now please observe, we want to know about the next state. Next state with x is equals to 0. If you are on state A, next state with x is equals to 0 0 and output with x is equals to 0 and output with x is equals to 0 0. X is equals to 1, state B, output 0. If you are on a state B, x is equals to 0, you will move to the state C. For x is equals to 1, you will remain in state B, output in both cases 0. If you are on a state C with x is equals to 0, you will move back to the state A, output 0. And if you are on a state C with x is equals to 1, you will move to state D, output 0. If you are on a state D with x is equals to 0, you will move to state C, output 0. If you are on a state D, x is equals to 1, you will move to state A, output logic level 1. How many of you are able to understand how to write this? Great. So the circuit what we want, for that we have completed the state table. Now I am going to write is modified state table along with the excitation table. So now please observe, we want to write excitation needed. Is it okay? How to find out the excitation needed? We have a input x, we have a input x, we have a input x, which has two possibility, either 0 or 1. We have a present state, we have a present state, and then we have a next state. Based upon present state and next state, we can write excitation on JK flip-flop. Okay, excitation on JK flip-flop. So please observe, beta ji. I can write it directly, but just to show you all the processes and to make you understand well, I have made like this. So this is your present input. So I'm writing present input x. Present state in terms of two flip-flops, we may have Q1, Q0. Next state, Q1 plus 1, Q0 plus 1. Excitation needed to JK flip-flop, J1, K1, J0, K0. Is it okay? Yes, sir. Now, please observe, beta ji. I am now in a final process of designing of the sequence detector. What you are learning with such a speed now is not possible with anyone. Okay. Mostly the people say that this is not the part which is going to ask in gate, but this is very important part, beta. Because only when you are able to understand this, you can able to solve the questions. Is it okay? So now please observe how to design. Until unless you are not study what is required, why you are studying, the topic is not get completed. So please observe here. We want to design a sequence detector, a decoder, so that we can have a secret message. Okay, conversation. So, okay, sir. Now please observe. So now we have a present input x, present state. With the present input x, x may be 0, present state 0, 0, x may be 0, present state 0, 1, x may be 0, present state 1, 0, x may be 0, present state 1, 1. Again, if you observe, x may be 1, present state 0, 0, x may be 1, present state 0, 1, x may be 1, present state 1, 0, x may be 1, present state 1, 1. Is it okay? Yes, sir. So present input and present state, we have total 8 combination possible with the present input and present state. Yes, sir. From 0 to 7. Yes, sir. Now, please observe here. Next state. I am interested to have next state. I am interested to have next state with x is equals to 0 and x is equals to 1. So now please observe here. If we are on state A, with x is equals to 0, next state A, output 0. Next state A, output 0. So I am using one more for output y. Output y. Okay. Yes, sir. Now please observe. If the present state is 0, 0, if the present state is 0, 0, if the present state is 0, 0, x is equals to 1. Next state is A is a 0, 0 state and output is 0. A is a 0, 0 state and output is a 0. A is a 0, 0 state and output is a 0. With the present state 0, 1, x is equals to 0. Present state 0, 1, x is equals to 0. Next state C state is 1, 0. C state is 1, 0. Output is 0. Present state 1, 0 with x is equals to 0. Present state 1, 0 with x is equals to 0. Next state A means 0, 0, output 0. So 0, 0, output 0. How many of you able to understand, beta ji? Present state 0, present state 1, 1 with x is equals to 0. Next state C is indicating 1, 0, output 0. C is indicating 1, 0, output 0. Present state A with 1, 1. Next state, present state A, x is equals to 1. Next state B means 0, 1. B means 0, 1. Output 0. Present state B, x is equals to 1. Next state B, output 0. Next state B, output 0. Present state 1 0, x is equals to 1. Present state 1 0, x is equals to 1. Next state D means 1 1, output 0. D means 1 1, output 0. Present state D, x is equals to 1. Present state D, x is equals to 1. Next state A, output 1. Next state A, output 1. How many of you able to understand? Great, sir. Now please observe, beta ji, we need to write down the excitation required onto the JK flip-flop. For that, we must need to know about the excitation table of the JK flip-flop. We all know about the excitation table of the JK flip-flop. So, I'm just writing the excitation table of the JK flip-flop in rough. Please observe everyone. I'm writing excitation table of JK flip-flop. So based upon present state and next desired state, we can find out the excitation needed on J and K. How many possibilities? 0 0, 0 1, 1 0 and 1 1. भाई साहब बताइएगा. And 1 1. Now if you remember, I told you for JK flip-flop, just take these two copy and then don't care, reverse it, 0 1, don't care. Now I'm going to utilize the excitation table information. To write the excitation table, excitation required on the flip-flop with which we want to design the sequence detector. So if the present state is 0, next required state is 0. Present state is 0, next required state is 0. 0, don't care is required onto the J1 and K1. Present state 0, next required state 1. Present state 0, next required state 1. 1, don't care is needed. Present state 1, next required state 0. Present state 1, next required state 0. Don't care 1. Present state 1, next required state 1. Present state 1, next required state 1. Don't care 0. Present state 0, next required state 0. Present state 0, next required state 0. 0, don't care. Present state 0, next required state 0. 0, don't care. Present state 1, next required state 1. Don't care 0. Present state 1, next required state 0. Present state 1, next required state 0. Don't care 1. In the same way, we have to observe Q0 and Q0 plus 1. So present state 0, next required state 0. 0, don't care. Present state 1, next required state 0. 1 0, don't care 1. 0 0 0, don't care. 1 0 1 0, don't care 1. 0 1 0 1 1, don't care. 1 1 1 1, don't care 0. 0 1 0 1 is 1, don't care. 0 1 is 1, don't care. 1 0 1 0 is don't care 1. In this way, we can fill the excitation table by observing Q1 and Q1 plus 1, and by observing Q0 and Q0 plus 1, we can find out the excitation needed onto the J and K. How many of you now able to understand up to this part? Great, sir. Next is to write the excitation equation and minimize it. Please observe, beta ji. We have to observe J1, K1, J0 and K0. So I am going to write the excitation equation of J1, K1, J0, K0. I am going to rub this rough part. Please observe here. In terms of X as a MSB and Q0 as a LSB, this is the binary of 0, 1, 2, 3, 4. Oh, what happened? What happened? Ari Baba. Now please observe. In terms of the binary 4, 5, 6, 7. Now please observe, beta ji. If you are writing the logical expressions required, excitation required on J1, what we are getting? Summation of m, where we are getting high, binary of 1, and don't cares are at 2, don't care are at 3, don't care are at 6 and 7. Was it okay? Similarly, K1, we have summation of m. We are getting 1 onto the binary of 2, and we are getting 1 onto the binary of 7. And don't cares are at 0, 1, 0, 1, then 4, 5. 4, 5. Similarly, you can identify for J0 as well, summation of m. For J0, we are getting logic level 1 onto the binary of 4 and onto the binary of 6. Okay. And don't care, we are getting onto the binaries of 1, 3, 1, 3, 5, 7. 1, 3, 5, 7. In the same way, we can write for J0 as well, K0 as well. K0, we are getting don't care. We are getting 1 at the binary of 1 and the binary of 3. 1, 3, 7. And we are getting don't care. Don't care are at 0, 2, 0, 2, 4, 6. 0, 2, 4, 6. Is it okay? Similarly, we have output Y. Y we are only getting high onto the binary of 7. Y we are getting only high onto the binary of 7. Is it okay? How many of you able to understand up to this part, beta ji? Great. Now with this, we can find out the logical expressions required by using K-map. Okay. So what we can use in the input side of the sequence detector, onto the input side, if we are using JK flip-flop, we can use either the present state or the present input. Present state or the present input. So in terms of present state, we have X bar, X present input, and present state Q1 bar, Q0 bar, Q1 bar, Q0, Q1, Q0, and Q1, Q0 bar. 0, 1, 2, 3, 4, 5, 6, 7. Now we have to observe for J0, K0, J1, and K1. So let's find out the minimized expression. So for J1, we have only present at 1 and don't cares are present at 2, 3, 6, 7. So 2, 3, 6, 7. We have only pair possible. With this pair, we are getting J1 to be equals to X bar Q0. Similarly, find out for J1. For J1, for J0, for J0, you have to observe this one, 4, 6, 1, 3, 5, 7. 4, 6, 1, 3, 5, 7. So we have a chord possible. J0 will become input X only. Now observe this one, 2, 7, 1, 4, 5. 2, 7, 1, 4, 5. 2, 7, 1, 4, 5. Okay. 2, 7. For K1, we have 2, 7, 0, 1, 0, 1, 4, 5, 0, 1, 4, 5, 0, 1, 4, 5. Okay. So now we have 2 possible, and with this we have K1 equals to X bar Q1 bar, sorry, Q0 bar plus of X Q0. So it is nothing but X XNOR Q0. Okay. Yes, sir. Now observe for K0. For K0, we are getting 137, 0, 2, 4, 6. 1, 3, 7, 1, 3, 4, 7, 1, 3, 7, 1, 3, 7, 0, 2, 4, 6, 0, 2, 4, 6. So if you observe, we have only 2 pairs possible, 1 pair and 1 chord. So a chord will give you X bar and pair will give you Q1, Q0. So this is your K0. So now we know about the required sequence detector. So your required sequence detector can be designed by using two JK flip-flop. So first I am using two JK flip-flop with this as J1, K1, Q1, Q1 complement, J0, K0, Q0, Q0 complement. Now you know about the root. Now please observe what is J1. J1 is X1, X bar Q0. J1 is X bar Q0. So it is coming with a D X bar Q0. Okay. J1 is X bar Q0. K1 is X XOR Q0. X XOR Q0. X XNOR, sorry. X XNOR Q0. Is it okay? Yes, sir. And we have J0 as X, J0 required as X, and K0 required as X bar Q1 Q0. So clock pulse. So basically the circuit what you want to design now, this is your desired sequence detector. This is your desired sequence detector. So we have a clock, input X, and we have output. So for output we have to observe the output expression. Output expression is high only on the binary of 7. So we can use min term. So min term of 7 can be represented as X Q1 Q0. So it can be represented as X Q1 Q0. We can use one AND gate with the input X Q1 Q0. This is your output Y. This is your required 1011 sequence detector. They may give you this circuit and ask you to identify the sequence detected by the circuit. They may ask you the input to any one of them. They may ask you to find out from the state table. They may give you the they may ask you about the expressions of any one of the input of the flip-flops. Didn't understand the last two step. Betaji, already it's a recorded video format, so you can rewatch as many times as you want na. So it's my humble request to you, please rewatch, because it's a lot of things. Even if I start doing from one particular step, you can't able to understand. So better to watch wherever you haven't understand na, just pause your video and then watch. Is it okay? Hoping all of you able to understand up to this part perfectly. So now onward you can design any desired sequence detector. Now you know about the Mealy model in a perfect way. Let's talk about Murray model as well. So what is the difference in the Mealy and a Murray model? The basic difference is the ending of your state diagram. Is it okay? Now please observe, first of all, in case of a Murray model, if we talk about non-overlapping, so in a non-overlapping Murray model, compare the last bit with the 1-bit state when the sequence is detected. So compare the last bit with the 1-bit state. However, in Mealy model, we are comparing the last bit with the reset state when the sequence got detected. Here, we will compare the last bit with the 1-bit state when the sequence got detected. Same, in overlapping of 1 bit, compare the last bit when sequence got detected to the 2-bit state. If it matches, okay, otherwise compare the last 1 bit with the 1 bit and so on. In case of 2-bit overlapping, compare the last 2-bit with a 2-bit state, 3-bit state. Compare the last 2-bit with a 3-bit state. Is it okay? If it matches, your state diagram ended with this 3-bit state. Otherwise, go back to the 2-bit state and 1-bit state and so on. So let's try to understand a Murray model as well. First, let us discuss about one question. To design a state diagram, let's take a example to understand. Okay. So draw a state diagram for Murray model sequence detector. Murray model sequence detector to detect sequence sequence 1011. Let us talk about this one. Okay. Yes, sir. So draw a state diagram. Draw a state diagram. Draw a state diagram for a Murray model sequence detector to detect a sequence 1011. I have chosen 1011 because already you have designed 1011 by using Mealy model. So you can have a clear differences between Mealy and Murray with this. Okay. And non-overlapping. Non-overlapping. So we have to design a Murray model non-overlapping by using Murray model, non-overlapping Murray model for a sequence 1011. See, everything is same. We want to design a sequence detector. In the sequence, 1-bit sequence detector, we have an input here and the output Y is available here. Onto the clock pulses, we have to observe the sequence of the input X obtained. Accordingly, your output Y indicates whether the sequence got detected or not. Output Y will become logic 1 only when the sequence got detected. So we want to design a sequence detector for sequence 1011. Okay. Yes, sir. First of all, we have to choose Murray model. So in a Murray model, can you tell me how many number of states required? Sir, number of states is equals to n plus 1, where n is the number of bits in a sequence. So we have 4 bit. So 4 plus 1, that is 5. Is it okay? Yes, sir. Number of flip-flops required will be equals to or less than 2 to the power of number of flip-flops required can be calculated by m less than or equals to 2 to the power n, 5 less than or equals to 2 to the power n. This indicate n must be equals to 3. So we need 3 flip-flop. Already we have designed this by using Mealy with the 2 flip-flop. But if you want with the Murray, we need 3 flip-flop. Is it okay? Yes, sir. Now, next is the state assignment. So I can let the states are, let the states A, B, C, D, E. So state A, you can consider 0, 0, 0, 0, 0, 1. It is not mandatory that you have to choose 0, 0, 1. You can also choose 0, 1, 0. There is no issue. 0, 1, 0, 0, 1, 1 and 1, 0, 0. So let us suppose these are the 5 states. We are giving the state names as this. For 3-bit, how many total number of states? Total number of states with a 3-bit is, note, total number of states with 3-bit is equals to 2 to the power 3, that is 8. So unused states are 2 to the power 3 minus we have n plus 1 in case of Murray model. For Murray model, so one can easily say, sir, we have 8 minus 5, that is 3. So these 3 states are considered don't care while designing. These the states are unused states are the unused states are 11 101 110 and 111. The output for these states considered as don't care. How many of you able to understand, Betaji? So, because these three states are never going to be appear. So for these three states, while designing, we will consider don't care. Is it okay? Yes, sir. Now we have only the used states. I am considering these 5 are the used states. Is it okay? Yes, sir. Now please observe here. Next is to construct state diagram. So first of all, we have to draw the state diagram. If we talk about a state diagram, we have a state A, state B, state C, state D, and state E. Now please observe here. Because in case of a Murray model, output is the function of present state only. So if you are on state A, the entire set of sequence is not got detected. If you are on state B, the entire set of sequence is not got detected. If you are in state C, the entire set of state is not got detected. If you are in state D, entire set of sequence is not got detected. If you are in state E, entire set of sequence got detected. So I am using this present state and output, because output is the function of present state only. Is it okay? Yes, sir. Rest of the thing goes in the same way. If you are in state A, we have to design the sequence detector for the sequence 1011. So if you get 1, you will reach to this state. Is it okay? So if you will get x is equals to 1, you will reach to state B. If you are getting x is equals to 0, you will remain in state A. If you have reached here, it means already 1 bit is already detected. If next x is equals to 0, you will reach to state C. If x is equals to 1, you have to check the 1 bit state. For x is equals to 1, you have to check the 1 bit state. This is a 1 bit state. 1 bit state. So 1 bit state is 0. If x is equals to next bit is 0, you will go to the next state. If x is equals to 1, then what happened? In this situation, you have to compare the last 1 bit with a 1 bit state. If it matches, remain in this state. Else, you have to go back to the reset state. So since it matches, so you will remain in this state. Is it okay? Now, when you have reached to state C, it means already 2 bits are being detected in the sequence 1, 0. Now, x can be 0 or 1. Is it okay? Yes, sir. If x is 0, then this is not the required set of sequence. Compare the last 2 bit with the 2 bit state. If it does not matches, compare the last 1 bit with the 1 bit state. If it matches, go to there. Otherwise, go back to the reset state. So since it is not matching, go back to the reset state. However, if x is equals to 1 and 2 bits are already being detected, so we have detected the correct sequence, move to the next state. Is it okay? Yes, sir. In the same way, if you are on state D, it means already 3 bits in a sequence got detected. Is it okay? Now, next input x can be 0 or 1. Yes, sir. 3 bits are already being detected in a sequence. 3 bits are already being detected in a sequence. If you got this is not the required set of sequence. So compare the last 3 bit with the 3 bit state. If it matches, remain in state D. Otherwise, compare the last 2 bit with the 2 bit state. If it matches, go there. Else, otherwise, you have to compare the last 1 bit with the 1 bit state, and then if none of them matches, then go back to the reset state. So since last 2 bit is matching with the 2 bit state, so it will come back to the reset state for x is equals to 0. For x is equals to 1, you have to go to the next state. Now the entire set of sequence got detected 1, 0, 1, 1. So entire set of sequence got detected. Is it okay? When entire set of sequence got detected, then Murray model for a non-overlapping suggests that last bit compare to 1 bit state when entire set of sequence got detected. So since entire set of sequence is detected, yes sir, since entire set of sequences got detected, so move the last bit to the 1 bit state. Now I have to compare the last bit with the 1 bit state. Since it is matching, so you have to end up to state B with x is equals to, next what we are getting, if we are getting 1, so 1. Is it okay? This is a non-overlapping Murray model, non-overlapping Murray model. How many of you able to understand? The same way can be utilized to design with the Murray model as well. In the Murray model, what we have to do? First, we need to draw the state diagram. After the state diagram, we have input x, which may be 0 or 1, and we have a states. Available state is from 0 to 4 only. Rest all states will be treated as don't care, and the outputs for them are treated as a don't care in the K map. Is it okay? And then we can check accordingly, fill the table, find out the excitation. If we want to design by using JK flip flop TD or your SR, accordingly we have to fill the excitation table, minimize it, and implement the logic circuit. So your circuit get designed by using Murray model. How many of you able to understand, beta ji? How many of you now able to understand? Beta Dhruv, you must have to check the yesterday video as well as today's videos, okay? Present and previous videos. So last two step I didn't understand. These step present in a previous video. So now this is the end of your sequential circuits. Hoping all of you able to understand. Only a very small step setup and hold time left out. So setup and hold time I am going to take tomorrow. Only with one question you will be able to understand how to solve the questions based on the setup and hold time concepts, and then we will move towards the A to D and D to A converters. So by tomorrow your entire syllabus is going to finish. Let me know by writing in the comment section, beta ji. These classes are very important, and it's very difficult to understand this particular topic. But if you just observe the video properly, and your concentration level will maintain, you can easily understand the entire cycles in just these two videos. Only 4 hours are sufficient, and you can design any desired sequence detector. You can solve any question based on the sequence detector. So please let me know by writing in the comment section how many of you able to understand this entire sequential part as well. So this is the end of your next chapter, that is sequential circuit. Tomorrow we are going to study about the A to D and D to A converters, and with that your entire digital electronics in this particular batch will get completed. Hoping you have enjoyed the lecture so far. All the notes are available on pw.live free batches. Is it okay? Also it is available on my Telegram, Varun sir PW. So thank you everyone, lots of love. Good night.